Welcome back. In this video, I'm going to solve exercises 1 to 4 of chapter 4. First exercise that we mentioned in the lectures, we have a norm space E and the convex subset C of E. First question, we have to prove that C is weakly closed if and only if it is strongly closed. The second question, we have to show that the weak closure of C is equal to the strong closure of C. And the last question is about the proof of Mazir's theorem. Okay? It states that if xn is a sequence that converges weakly to some limit x, then we can find another sequence yn made of convex combination of the elements of the sequence that converges strongly this time to the same limit. Okay, so I'm not saying that xn is converging strongly, but because yn is a different sequence. So let us start with the first question. So a weakly closed set is always a strongly closed set, even if it's not convex, because the strong topology or the norm topology is bigger than the weak topology by definition. So if a set is weakly closed, then its complement is weakly open, and therefore the complement is strongly open as well, and therefore the complement is strongly closed. Now, so the converse is not true in general without any additional assumption, but here we have an extra assumption that C is convex. This is very important. So we consider now a convex set C which is strongly closed, and we have to prove that it is weakly closed. How do we prove that? One way is to prove that the complement is weakly open, or open with respect to the weak topology. And how do we prove that? We prove that the complement of C is a weak neighborhood of all its points. Okay, so we pick an arbitrary point x0 on the complement of C, and we have to find a neighborhood in the weak topology that contains x0 and or a weakly open set that contains x0 and is contained in the complement of C. Now, if x0 is in the complement of C, then x0 is not in C, so the singleton x0 and C are disjoint, and the singleton 0 is compact and convex, and C is closed and convex, strongly closed and convex. So we can apply the second geometric form of the Banach theorem, and accordingly, there exists an element in the dual F, a closed hyperplane, if you like, that separates x0 and C. So, otherwise stated, there is an element in the dual and a number alpha such that f of x0 is less than alpha, strictly less than f of x for all x in C. This is the separation theorem. So, we do as in the proof that the weak topology is Hausdorff. So we take the inverse image under f of the open interval minus infinity alpha. F is linear and continuous, strongly continuous. Therefore, it remains continuous with respect to the weak topology, because the weak topology is the smallest topology that makes these maps continuous. So f is continuous with respect to the weak topology. Therefore, the inverse image under f of an open set of R is open in the weak topology. So U is a weakly open set that contains x0, because x0 is in U. And U is contained in the complement of C, because if x is in C, then f of x is strictly bigger than alpha, so it cannot be in. So x cannot be in U. And that's it. So therefore, E without C is a neighborhood of x0, and since x0 was arbitrary, this means that the complement of C is a weak neighborhood of all its points, and therefore it's weakly open. Okay, so second question, we have to prove a double inclusion. C bar, so we have here to distinguish between two kinds of closures because we have two topologies now. So the strong closure of C will be denoted just by C bar as usual, and the closure in the weak topology will be denoted by C bar weak, or if you like, C bar of sigma EE star. So by definition, C bar weak is the smallest weakly closed set that contains C. Now, so this is a weakly closed set. In particular, it's a weakly closed set that contains C. But a weakly closed set is a strongly closed set, even if it's not convex. So C bar weak is a strongly closed set that contains C, but C bar is the smallest strongly closed set that contains C, and therefore C bar is contained in C bar weak. Okay, so this is true. This inclusion is true even if C is not convex. Now, for the converse, we reason in a similar way. So C bar is a strongly closed set and convex. So by A, it is weakly closed. But by definition, C bar weak is the smallest weakly closed set that contains C. Therefore, C bar weak is contained in C bar. So we have a double inclusion, and therefore we have equality. Now, if C is not convex, you don't necessarily have equality. Okay, so the first inclusion is true, but not the second one. So for example, if you recall in the lectures, in an infinite dimension norm space, the weak closure of the unit ball, we proved that the weak closure of the unit sphere is the unit ball. Whereas the strong closure of the unit sphere is the unit sphere itself, because the unit sphere is closed, is strongly closed. Yeah, so don't have equality in this case. Now, third question, we have a weakly convergent sequence xn that converges weakly to x. We consider the convex hull of the range of xn. Okay, so here we have to distinguish a little bit between the sequence and the range of the sequence. The sequence is just a list or an application from n to e, but the values taken by the sequence is just the range, x1, x2, etc. Now, this set is not convex, but we can consider the smallest convex set containing the set, and this is called the convex hull of the set. Okay, so it's by definition a convex set. Okay, and there's a characterization of this set in chapter 2. There's an exercise where we prove that the convex hull of a set consists of exactly the convex combinations of the elements of the set. Probably know that from second year, but you can always do that exercise. So now, since xn converges weakly to x, this means that x belongs to the weak closure of the set. But the weak closure of the set is contained in the weak closure of the convex hull, because it's bigger. So x actually belongs to C bar weak. Okay? But C bar weak is just C bar, according to what you said, because C is convex. Okay? So what does it mean? So since the strong topology is metrizable, by definition, we know from proposition 0.3 in the metric case that if an element is in C bar, then we find, and the space is metrizable here, then we can find a sequence in C that converges strongly to X. And that's it. This is the sequence that we call Yn. Yn is a sequence in C, so it's made of convex combinations of the Xi. And that's it. And actually, we can prove more. More is true. We can choose the sequence Yn so that it is a convex combination of the elements starting from the nth index. Okay, so we don't need the first. So each Yn is a convex combination of xn, xn plus 1, and so on. Okay, finitely many terms, of course. Just modify this reasoning a little bit. And we used this fact actually at some point in the lectures. Okay, but I suggest that you do that on your own. Just modify a little bit this reasoning here. Okay, so this is Mazir's theorem. Okay, so this concludes exercise 1. Exercise 2 that we already mentioned in the lectures. We have two Banach spaces E and F and a linear operator between E and F. We have to show that three conditions are equivalent. When we equip E and F with their norm topology, first condition states that when we equip E and F with their norm topology, then T is continuous. So we say that T is continuous strong, because you put the strong topology on E and the strong topology on F. The second condition states that when we equip E and F with their weak topologies, then T is continuous. So we say that T is continuous weak, because you put the weak topology on the source and the target space. Now, the third condition, we put on the source space the norm or the strong topology, and on the targets set or space, we put the weak topology. So in this case, we say that T is continuous strong weak. Okay. And there is a fourth permutation, if you like. What happens if we put the weak topology on the source space and the norm topology on the target space? Then we talk about continuity weak strong. And continuity weak strong is in general not equivalent to. So the first three conditions are equivalent. This is what you have to prove. And in the second part, you have to prove that continuity weak strong is equivalent, actually stronger than these three conditions. So it means continuity strong, and something very restrictive, that T is a finite rank operator, which means that the image of T is a finite dimensional subspace of F. Okay, so this is something very restrictive. Okay, so step by step. Now, so first part. Observe that condition 1 implies condition 3, even if T is not linear. Okay, why? Suppose that T is continuous strong. This means that the inverse image of a strongly open set here is an strongly open set here. Okay. And so now in particular, if we take a weakly open set in F, a weakly open set is an open set, is a strongly open set. Therefore, its inverse image is a strongly open set, so it's here. Okay. So 1 implies 3, and even if T is not linear. Okay. And similarly, 2 implies 3. Why? Because if the inverse image, if 2 is satisfied, then the inverse image under T of a weakly open subset of F is a weakly open subset of E, and therefore it's a strongly open subset of E. So 2 implies 3, even if T is not linear. Okay. So we have already 2 of the implications that holds in general. Okay, so we'll do a circular proof. 1 implies 2, 2 implies 3, we did it. So just have to prove that 1 implies 2 and 3 implies 1 in the first part. And in the second part, we just do a double implication. Okay, so 1 implies 2. We have to go back to proposition 4.2 and the definition of the smallest topology making continuous a collection of maps. So here we consider the weak topology on F. So in the notation of section 4.1, this is what we called X, this is Y I, and this is Z. Okay. Now, what is the collection of maps that this topology make continuous? These are by definition just what we call phi sub F, which is just F, where F is an element in the dual of capital F. Okay, so the weak topology sigma F star is by definition the smallest topology making these maps F, which are linear and continuous, continuous. Okay, so to prove, so we have this diagram actually. To prove that T is continuous in these topologies, we have to prove that the composition between phi F and T is continuous. This was the object of proposition 4.2. Okay. So consider now, instead of T, we compose T with this collection of maps, okay, where F is in the dual of capital F. Now, what is this map? This is just F composed with T. So it's F of T of X that you can write in this way, or F parenthesis Tx. Now, this is, of course, a linear map from E to R, because just the composition of 2 linear maps, and it's bounded, moreover, because if we take the values as an R, so the norm on R is just the absolute value. So the absolute value of phi F of T at X is just the absolute value of this number. So this is less than the norm of F times the norm of Tx by the fundamental operator inequality. And since T is continuous strong, then the norm of Tx is less or equal than the norm of T times the norm of X. Therefore, the absolute value of phi F of T at X is less than a constant times the norm of X. So we get now a linear bounded operator from E into R. And therefore, so this is continuous, it's bounded, so it's therefore, and the weak topology, since the weak topology on E now is the smallest topology that makes these maps continuous, so in particular, this map is continuous relative to the weak topology. Okay. So this concludes 1 implies 2. Now, 3 implies 1. We use the closed graph theorem. So to show that T is continuous strong, we show that the graph of T is strongly closed. Okay. So how do we prove that? We take an element in the closure of the graph and prove that it's in the graph. So if we take an element xy in the closure of the graph, strong closure of the graph, therefore we know from the metric topology that there exists a sequence in the graph. So it's of the form xn txn that converges to xy. So this means that xn converges to x and txn converges to y. So I have to show that y is equal to tx. Now, strong convergence, as we know, implies weak convergence. So therefore, xn in particular converges weakly to x, and txn converges weakly to y. And since T is continuous weak by assumption, then in particular it's weakly sequentially continuous, if you like. So Txn converges weakly to Tx. So what do you have now? We have Txn converges weakly to Y, and Txn converges weakly to Tx, but the weak limit is unique because the topology is Hausdorff. Therefore, Tx equal to Y, Tx equal Y, and therefore xy is in the graph. So we took an element in the closure of the graph and we proved that it's in the graph. So the graph is closed in the strong topology, and therefore T is continuous, strong. So just what the continuity that you know from second years, the boundedness, if you like. Okay, so now the second part, 4 and 5. So here we deal with the continuity weak strong. Okay, so let us prove that 5 implies 4. So we have that T is continuous strong, and the dimension of the image of T is finite. Okay, so we have to prove that T is continuous weak strong. So we take a strongly open set in the image of T, and since T is finite dimensional, the weak topology and the strong topology coincide. So actually this O set O is weakly open. But so since T is continuous strong, it's continuous weak. Therefore, the inverse image of O under T is weakly open. And that's it. So T is continuous weak strong. So the inverse image of a strongly open set is a weakly open set. This is easy. Now, 4 implies 5, a little bit less trivial. So we assume that T is continuous weak strong, and we prove that it's continuous strong, and the range of T is finite dimensional. Now, if T is continuous weak strong, then it's continuous weak. Okay, and this is true even if T is not linear, because if it's continuous weak strong, it means that the inverse image of a strongly open set is a weakly open set. So in particular, the inverse image of a weakly open set is a weakly open set because the weak topology is contained in the strong topology. Okay, so this is true even if T is not linear. So the point here is now to prove that the image of T, or T of E, is finite dimensional. Okay, so take a positive number epsilon, and we just write the condition of continuity weak strong at 0, just at 0. Okay. So what does it mean that T is continuous weak strong at 0? By definition of continuity that we explained in chapter 0, this means that for every neighborhood of T0, which is 0, every strong neighborhood. Okay, so it's just this is the can take the ball of center 0 and radius epsilon. For every strong neighborhood of 0, we can find a weak neighborhood of 0, such that T of that neighborhood V is contained in this ball. So there exists a weak neighborhood V of 0, such that T of X is in the ball of center 0 and radius epsilon for all X and B, because here we take as a neighborhood of 0 in the strong topology just the ball of center 0 and radius epsilon. Okay. Now, since V is a weak neighborhood of 0 in E, so V contains actually a fundamental neighborhood that we discussed in section 4. So we can assume that V is of the form, so there are finitely many elements F1, Fk in the dual of E, and the positive number delta. I cannot take epsilon because it's already taken. So we can assume that V is of this special form. So this kind of sets plays the role of balls in the weak topology. It's not a ball. Okay. So, and just now consider the set M of X such that Fi vanishes at X for all I between 1 and K. And note that now M is a subset of V, because if Fi is 0, then of course an absolute value of I is less than delta. So we encountered this kind of situation when we discussed the weak topology. So this is why actually that in infinite dimensional spaces, weakly open sets are unbounded because they contain a subspace. Okay. So M is a subspace of E, which is contained in this weak neighborhood. Okay, now we claim that the operator T vanishes on M. Okay, so Tx equals 0 for all x in M. So consider an arbitrary element x in M, and consider an arbitrary number alpha in R. Okay. Since x is in M, then Fi of x is 0. Okay, and since Fi is linear, because it's in the dual, right, of E, so Fi of alpha x is 0. Okay, for all I between 1 and k. And therefore, the absolute value of Fi of alpha x is less than delta, and therefore alpha x is in V. And by our choice of V tells us that in this, if alpha x is in V, then T of alpha x is less than epsilon. And by linearity, I can put the alpha outside. So if I put alpha outside the T and then outside the norm, I get absolute value of alpha of Tx norm is less than epsilon. So when I divide by the absolute value of alpha and let alpha tend to infinity, divide by absolute alpha. Okay, so we get Tx is 0. And this proves the claim. Okay, now we observed in the lectures that the codimension of M is finite. And this was something not trivial, actually. Actually, this part is optional. So if you don't understand all the details, it's okay. But just for completeness, it's good to understand what is continuity weak strong. Okay, why we do not include it in the other conditions. It's because it's something stronger. So the codimension of M is finite. So this means that M has a topological complement, which is finite dimension G. Okay, and now since G is finite dimensional, then T of G is finite dimensional. But since T vanishes on M, then T of E equal to T of G, as you know from algebra. So this means that T of E is finite dimensional. Okay? So continuity weak strong is more restrictive than continuity strong, or just boundedness, if you like. So this concludes exercise 2. Exercise 3 is actually just a consequence of Hahn-Banach theorem in Rn+1, and we did a special case of it in chapter 2. Okay, we in chapter 2 just had two functions, actually, phi and phi1. Here we have a vector space E and n+1 linear maps from E to R. Now we don't put any norm on E. Okay, so it's just any vector space. So this is actually an algebraic lemma that you probably encountered in a course on algebra, actually. So we assume that if all phi I vanish at x, then phi vanishes at x. Or otherwise stated, the intersection of the kernels of phi I is contained in the kernel of phi, if you like. Okay. So we have to show that, so the conclusion is we have to show that phi is a linear combination of phi 1, phi n. Okay. So, and hence, we consider the map from x to Rn+1, whose components are phi of x, phi 1 of x, phi n of x. Okay. We can rearrange them, it's not really important. We could write phi 1 of x, phi n of x, and then phi of x. This is what we did in exercise 1 of chapter 2. Doesn't really matter. So here we have a vector of linear maps, so it's linear itself. And the fact that if you consider the point 1, 0, 0, 0, it doesn't belong to the image of F, okay? Because all the components are 0, but the first one is not 0. So the point of coordinates 1, 0, 0 is not in the image of F. So therefore, we can, as we did in chapter 2, we can separate the convex compact set singleton A from the subspace, which is the range of F. Okay? So it's a subspace. So it's a really particular case of Hahn-Banach theorem because we are just separating a plane or a hyperplane, if you like, with a point. So we are not using the full strength of the Hahn-Banach theorem. Okay, so yeah, so this is actually what we was saying. So therefore, there exists a linear map. Now I can call it F actually because I use different notations for the for the maps. Okay, so there's a linear map that separates the point 1, 0, 0 and the range of f. Okay, and now what do we have? So we have a linear map which is bounded from below on a subspace, and we know from chapter 0 that f must vanish on the subspace. Okay. So we already encountered this kind of reasoning. It's important to work on a subspace, because if we are just working on a convex set, it's not true. Okay, so subspace is a particular case of a convex set. It's really particular. Now, since f is linear, it's a linear map of n+1 variables. So it's a linear map from Rn plus 1 into R. So it's necessary of this form, lambda 0 x0, lambda plus 1 lambda 1 x1 plus lambda n xn, as we know from chapter 2. Okay, because this is just a linear map from Rn plus 1 into Rn. So it's a dot product, if you like, between the vector lambda 0, lambda 1, lambda n, and the vector x0, x1, xn. So since f vanishes on the subspace image of f, then in particular, so when I replace the arguments of x of capital F by phi of x, phi 1 of x, phi n of x. So the fact that f vanishes on the image of f means that lambda 0 of phi x plus lambda 1 of phi x plus etc. lambda n of phi n of x is 0 for all x in E. And now if I evaluate f at the point 1, 0, 0, I just get lambda 0. Okay. So, but by the separation property, f of 1, 0, 0 is less than alpha. So lambda 0 is strictly less than alpha. And the right-hand side is just 0, actually, according to what we said. So therefore, in particular, lambda 0 does not vanish, strictly negative, actually. So I can divide, therefore, by lambda 0. And therefore, I can solve this equation in terms of phi x. So phi x is just minus lambda 1 over lambda 0, phi 1 of x, plus minus, etc., lambda n over lambda 0, phi n of x. Okay, so this means that phi is a linear combination of phi 1 through phi n. So this is a very useful algebraic lemma that you probably encountered in another course, but it's okay. So we can prove it by using a particular case of the Hahn-Banach theorem. Okay, so this concludes exercise 3. Now, the last exercise, we have a normal space E and a linear map from that I call Xi, from the dual of E into R, which is linear and continuous for the weak star topology. We have to show that Xi is in the image of J, where J is the canonical injection from E to the bidual. Okay, standard notation. So otherwise stated, Xi is equal to Jx for some x in E. Now, as you know, not every Xi in the dual of E double star belongs to J of E. So this is true if E is reflexive. Okay? J is not necessarily surjective. Okay. So what we want to prove actually is the converse of the implication that if Xi is in J of E, then Xi is continuous for the weak topology. And this follows precisely from the definition of the weak star topology, because the weak star topology makes continuous all these maps that live in J of E. So here we have to prove the converse. We have to prove that if Xi is continuous for the weak star topology, being linear, of course, then Xi must belong to the image of J, of the canonical injection. Okay, and this is not difficult actually, because we just go back to the definition of continuity as we did before. So we just consider the continuity at 0. What does it mean to say that Xi is continuous at 0? And Xi being linear, it means that for every neighborhood of Xi of 0, which is 0, we can find a neighborhood V of 0, as we did before, whose image under Xi is contained in this. Here we just take the interval, the open interval minus 1, 1 in R, because Xi takes value in R. Okay, so here, if you like, this is the open ball of center 0 and radius 1 in R, which is just an interval. Okay, So same kind of reasoning that we used before. So here we take just the epsilon equal 1. We don't need more than 1. Okay, so take epsilon equal. You could take any epsilon if you like. 1 is enough. So we find a neighborhood V of 0 in the weak star topology, whose image under Xi is contained in this open interval. So Xi f in absolute value is less than 1 for every f in V. Now, as you guessed, we can assume that V is of this special form because this is a basis of neighborhoods of 0, as we discussed in section 4.3. So actually, V contains a set of this form, but so we can assume that V is of this form. Okay? So there are finitely many elements Xi in E, such that f of Xi in absolute value is less than epsilon for all I between 1 and k. And now I claim that if f vanishes at all Xi, then necessarily Xi vanishes at f. And then I will use the previous exercise. So suppose that f vanishes at all Xi. Then n of f Xi is 0. Multiply by n. And therefore, in particular, the absolute value of nfi of Xi is less than epsilon. So nf belongs to V. And therefore, Xi of nf is less than 1 according to our condition. What does it mean that Xi of nf is less than 1? Since Xi is linear, I can put the n outside and then divide by n. So I get Xi f in absolute value is less than 1 over n. But this is true for every n. So letting n tend to infinity, you get Xi of f is 0. So we proved this claim. And according to the previous exercise, this means that so I can rewrite this condition instead of f of Xi, I can write it as jxi of f. Okay. Yeah. Same thing, but I call it xi I. It doesn't matter. But it's really jxi of f. So therefore, okay. Anyway, so if we call fxi, so f this term actually is not only linear in xi, it's linear in f. Okay, so we call it xi I. Doesn't matter. So if you call it xi of f, then the condition, the claim that we proved, is equivalent to this implication. If xi I, if all xi I vanish at f, then xi vanish at f. Okay? And according to exercise 3, xi is a linear combination of the xi I. So we find k elements alpha I, such that xi is this linear combination of the xi I. Okay, so this means that xi of f is sum of alpha I xi I of f. And so I just go back to the definition. Xi I of f is just f of xi. And by linearity, so the linear combination of the images is the image of the linear combination because f is linear. And now I just call this x. So if I call this a linear combination of xix, I just write fx, and this is just jx of f. So we proved that xi of f is equal to jx of f. This is true for every f in the dual of, and therefore xi is equal to jx. So xi is in the image of j. Okay. So we could have written actually jxi of f, get the same thing. So okay, so this concludes exercise 4 and this video. Thank you for your attention and see you next time.